Next, paramagnetism. Okay. So, paramagnetic materials are such materials for which the individual atoms possess permanent magnetic dipole moments. Now, if a bar of paramagnetic material is placed in the external field, the field lines gets concentrated inside the material and the field inside is enhanced. The net dipole moment is induced in the direction of the external field. And when these paramagnetic substances are placed in the external non-uniform magnetic field, then they have the tendency to move towards strong magnetic field region from weak one. Okay. Now see, here in figure, it is represented when the paramagnetic sample is placed in the external field, then its dipole moments, say individual atoms possess permanent dipole moments, but all those dipole moments are randomly oriented. So when we take the vector summation of all these, then net magnetic moment, that is 0. And therefore, this substances does not show you the magnetic properties. But as soon as we place it in the external magnetic field, all the dipole moments will try to align themselves in the direction of that external field. Okay. So inside the sample, the magnetic field developed, that will be in the direction of the external field. Therefore, inside the substance, magnetic field becomes stronger one. It implies that we can say this thing, the field lines concentrated inside the material. Now see here, due to the alignment of these dipole moments, the south pole induced in the sample, that will be towards the north pole of the external agency, and the north pole in the sample will be induced towards the south pole of the external agency. Therefore, when we think about the non-uniform magnetic field, these poles will experience attractive force, and attractive force towards the strong magnetic field region, that will be dominant one. Therefore, the tendency of this particular sample, that is to move towards the strong magnetic field region. Clear to all of you? Now, some paramagnetic materials are aluminium, sodium, calcium, oxygen at STP, and copper chloride. Now, experimentally, we can observe this thing, the magnetization of the paramagnetic substance, that directly proportional to the intensity of the external magnetic field. As we increase the external magnetic field, more and more number of magnetic dipole moments will align in the direction of the field of that substance. So as the number of dipole moments align in a particular direction increases, then we can say the magnetization of that substance is increasing one. So M directly proportional to B0, as well as M proportional to 1 upon temperature. As we increase the temperature, then due to thermal excitations, the randomization of the dipole moments increases. And if randomization increases, then the magnetization decreases. So resultantly, we can write M, the magnetization proportional to B0 by T. So we can write M, that is C B0 by T, where C, that is Curie's constant on behalf of the name of the scientist who experimentally studied all these things. Okay. Now, here on right hand side, multiply and divide by mu 0. So C into B0 mu 0 upon mu 0 T. But here B0 upon mu 0, that we can write H, the magnetic intensity. Now take this H on left hand side. So M by H, that is C mu 0 by T. But M, that is chi H. So M by H, that is chi. So chi, that is C mu 0 by T. Clear up to this one? Now this equation that is known as Curie's law. After its discoverer Pierre Curie, the constant C is called Curie's constant. Thus, for a paramagnetic material, both chi and mu r depends not only on the material but also on the sample temperature. As the field is increased or the temperature is lowered, the magnetization increases until it reaches the saturation value Ms, at which point all the dipoles are perfectly aligned with the fields. Beyond this, the magnetization of sample is not possible because all the dipole moments are now aligned. So beyond this, Curie's law is no longer valid. Clear to all of you, beta?